Welcome everybody. My name is Serena Elisa Ponta and I am a senior researcher at SAP Security Research. I have been working on open source software security since 2013 and I spent most of these years on the problem of publicly known vulnerabilities in the open source software dependencies of applications. The main outcome of this work is Eclipse study, which is a tool that we open sourced in 2019. My goal for this presentation is to give you my view on why we focused and still focus on the security of open source software dependencies by showing what we did and what we are doing. And I say we because, of course, I'm not working alone. We are now a team of 5 researchers at SAP, and we also collaborate with universities and take part in European projects. I will start with some context on the relation between commercial applications and open source software components. I will then talk about two major threats that their coexistence poses. So I will talk about open source supply chain attacks and dependencies with known vulnerabilities. I will then spend some time on the code-centric approach we devised to detect, assess, and remediate known vulnerabilities, which is the approach that was implemented in Eclipse study. And then I will discuss open problem and direction. So, commercial software products embed open source components and more in general depend on open source components. This should not come as a surprise. You may look at one of the many reports about the usage of open source and you will always find very high percentages showing that open source is omnipresent. In 2020, Synopsys reported that 99% of the code bases that they audited contained open source. And it's not just widespread. In fact, open source components may actually constitute the vast majority of the code base of an application. In our work, we observed that for Java application, they may represent more than 90% of the code base of an application. In 2021, Synopsys reported that in average an application has more than 500 open source components with an increase of more than 250% over 5 years. So we are in a situation where the newly developed code is just a small fragment, and this is usually represented as an iceberg, where the new code is what is visible on top of the water, but what is below is far bigger, and what is below is the code coming from open source software components. Let's have a closer look at what is below. What we have is actually a graph of dependencies. So given an application, a developer reuses some already existing functionalities, importing some functions from some libraries, which represent the direct dependencies of the application. But then dependencies have dependencies on their own, the transitive dependencies. And the result is a graph that may have hundreds or even thousands of nodes. And as you may imagine, this graph will have duplicates, conflicts, and a level of complexity that is usually handled by automated build systems. So tools like Maven or NPM handles all this complexity in a transparent way for the developer. But does this mean that there is no issue? Of course not. This is another view of an application that clearly shows how fragile the entire system is. In fact, the quality of the overall application depends on the quality of each component. And if everything is handled out transparently, then there are no guarantees that each component will meet the expectation in terms of maintenance, performances, bug fixing, and also security, which is our focus. So we are in a situation where a developer is creating an application that he thinks he owns, but actually the libraries he is using are bringing in the entire graph, which also implies thousands of other contributors. And these people may have different competencies, different skills, different targets, different attitudes. So the two main threats in this context are open source supply chain attacks and dependencies with known vulnerabilities. In both cases, the goal is to attack an application via its open source dependencies. But in the one case, this is done by sneaking in some malware, whereas in the other case, this is done exploiting the publicly known vulnerabilities, which result from some bugs that a benign developer may have accidentally introduced. So let's start from the open source supply chain attacks. So in this case, we have adversaries that try their best to hide and inject malicious code by looking for the weak spots in this complex architecture and of course in what is used to create it. So in general, in a supply chain attack, we have that the attacker is trying to compromise the vendor infrastructure so that it can infect the legitimate software and have the malware distributed through the vendor's channels. In the flavor of open source supply chain attacks, rather than targeting the infrastructure itself, the building blocks are attacked. So the idea is to inject the malicious code in the open source dependencies so that the malware is then executed by the application that depends on them. Of course, this can be done by attacking the dependencies that will become part of the application once released, so that will be executed at the application's runtime, but it's not sufficient to just look at those. In fact, anything that gets executed also at development and build time can very well infect the application, can steal the developer credential, or can even infect the build infrastructure itself. Let's look at an example. This is a successful attack that was run against the package event stream in 2018. So event stream is a quite popular package. It has more than 1.5 million downloads per week and at least 1,600 packages using it. What happened is that the original developer was contacted by email by a user offering to help maintaining the project. And to hand over the ownership of a project is not uncommon in open source because it may very well be that the original developer cannot or doesn't want to maintain it any longer. And so what happened is that the original developer handed over the ownership. The guy added a dependency on a malicious package. It's not uncommon to add a dependency, and on top of it, the dependency was doing what it was supposed to do. And if this was not enough, the malicious code was not part of the source code. So even reviewing the sources of the project that was added a dependency would not have helped because the malicious code was only present in the package that was published in NPM. And this is already a good hiding, but in fact, there is one more step because the malware would only run in a specific context. So it would only run in the context of a release build of the Bitcoin wallet copy. So this example already shows to which extent attacker may go to hide and have their malware run. A review of real-world attacks that were run between 2015 and 2019 is available in the Backstabber knife collection. In there, there is an analysis of such attacks in terms of targeted ecosystems, techniques used, temporal aspects, and many others. And the resulting dataset is available. It's sufficient to write an email to the emails reported in the slide, which are the two first authors of the corresponding publication Backstabber knife collection. And you will get access to the GitHub repository hosting the dataset. As of today, it has more than 1,100 packages. And for the cases where the malware, where the malicious code where it was possible to obtain it, it is also available. One of the main outcomes of this work was the creation of an attack tree. This attack tree provides basically a structured overview of the techniques that can be used to inject and run malicious code in real-world attacks. At the root, we have the goal. So the goal is to conduct an open source supply chain attack, and the children contain alternative techniques that can be used in order to achieve the parent goal. At every layer, we have a further specialization of the technique. So if we take, for example, the event stream attack, we can map the techniques used therein on the tree, and this is represented by the red node. So the goal was to conduct the open source supply chain attack, and this was done by adding a dependency. So the code base of the event stream package was modified. So they injected the malicious code directly in the sources by adding a new dependency on a malicious code. This was done by contributing as a maintainer, and this was possible because the guy became a maintainer. On top of providing this structured view of the attacks, on the nodes of the attack tree are mapped to safeguards. So it's possible to select a safeguard and see which techniques it would fight. So in this case, for example, by manually reviewing the source code, it would be possible to prevent this kind of attacks like the one of event stream, even though it must be noted that to manually review the sources, especially when the attacker tries to add the malicious code, is a very time-consuming activity. There is an ongoing survey. It's an anonymous survey. The goal of the survey is to collect feedback on the attack tree. So to get feedback from experts in the domain in order to evaluate the tree in terms of structure, completeness, and usability, and also to assess whether the safeguards that are mapped are useful and how much costly they are. So if you have experience in the domain, I would like to encourage you to follow the link at the bottom of the slide and complete the survey. It would be very much appreciated by my colleague, as this work will be part of his PhD thesis. So what are the takeaways for open source supply chain attacks? So first of all, we can for sure say that the attack surface is quite big, because we have a huge number of dependencies, hundreds if not thousands. We have for sure thousands of actors in the picture, and we have complex build systems and infrastructures. On top of it, all dependencies have to be considered, not only compile and runtime, but also test and build dependencies have to be carefully analyzed. And the truth is in the downloaded packages. So it's not just possible to look at the sources in the GitHub repositories of the used projects. It's necessary to look at the actual code that gets downloaded and executed. So it's not surprising that the number of supply chain attacks is growing. In 2020, Sonatype reported an increase of more than 400% in just 1 year. It looks like the targeted ecosystems are Python, Node.js, and Ruby, so the main targeted ones. But in our view, this may also be due to the fact that other ecosystems like the Java one may not have been analyzed systematically until now. So this is a very active field of research that definitely requires attention. While open source supply chain attacks are a rising threat, I would say that dependencies with known vulnerabilities is a well-known one. In fact, it's in the OWASP top 10 since 2013. In this case, the attacker does not inject malicious code, but is exploiting publicly known vulnerabilities which are already there in the components because of some bugs that some developer introduced, and that in most of the cases is already fixed. So a patch is available. Still, there are some prominent examples showing that publicly known vulnerabilities are exploited. And the most famous, I would say, that is the Equifax data breach. This happened in 2017, when the personal information of almost 150,000 people were stolen, including social security numbers, birth dates, addresses, and the like. What happened is that the attacker gained access to the internal servers on the Equifax corporate network by exploiting a known vulnerabilities of the Apache Struts library that was used as framework for one of their web applications. The vulnerability was known and the patch was available. So the question can be why they simply didn't update. And the reason is that to update is not that simple. In fact, we have to consider which is the life cycle phase of the application and the deployment model. If we think about an application that is in development, it should be easier at least to update a dependency. But if we think about an application that is in maintenance and that is running on premises, to update is a completely different story. So it for sure requires downtime, but on top of it, we have to consider that to update a dependency may bring in some breaking changes for the application. So it may require to apply some changes to the overall application. And on top of it, it may not be that easy to understand what is the impact of the change, because in 78% of the cases, the vulnerabilities are intransitive dependencies. So dependencies that are not used directly from the application. So the hard reality of vulnerability management is that this is a continuous process that goes on and on. So what it requires is first to check for new vulnerability disclosures. That hopefully is an automated step. And then it requires to understand whether the found vulnerabilities are true or false positives, hoping not to have false negatives. Then the findings needs to be mitigated, which can be easy when a simple update is possible, but it could be very expensive when, for example, a patch is not available or there is a major release update that requires to change the application in multiple ways and in multiple places. And once the mitigation is in place, the patch can be released for the overall application, and to put this in place, again, can be easier in the case of cloud environments, but can be expensive yet again for on-premise solutions. What is available in order to support this process of vulnerability management? There are two main approaches for open source vulnerability scanners. The first one is based on metadata. So the idea is to map vulnerabilities to the packages that are used as dependencies of an application by using their names and their versions. One example of these tools is the OWASP dependency check. Another approach is the code-centric one that we first proposed in 2015. Here, the idea is to detect vulnerabilities by the presence of the vulnerable code, no matter the package. And the vulnerable code is the code that was changed in order to fix the vulnerability. So once detected, then we can also support an impact assessment by establishing the reachability of the vulnerable code using both static and dynamic analysis. And having this deep knowledge about how the application uses the dependencies, in this approach, we also define some update metrics that can be used by the developer in order to decide how to remediate the vulnerability. An implementation for Java and Python of the approach is Eclipse Steady, which is released as open source, and it was used to scan more than 2,000 projects at SAP within CI/CD pipelines and with a load of more than 150,000 scans per month. Before digging in the details of the code-centric approach, let's first see what are the major issues with the metadata approach. This is a vulnerability as they appear in the National Vulnerability Database, NVD, which is the largest publicly available repository for known vulnerabilities. This is CVE 2018-13-371. CVEs are the identifiers usually used for identifying vulnerabilities. So we have a description talking about the vulnerability, and then we have a severity score, the CVSS. We have references that in some cases, but not all, may point to the commit fixing the vulnerability. And then we have a list of affected products. In this case, it's pointing to Eclipse Mojarra using the CPE standard. And the description and the affected products both says that this vulnerability is fixed in version 2.3.5. So this looks neat. However, as you may imagine, maintaining this kind of information with the human as the main player is an error-prone activity. In fact, the vulnerability is not fixed in version 2.3.5. It's actually fixed in version 2.3.7. And this is something we found with our code-centric approach, as we found that version 2.3.5 and 2.3.6 did not contain the fix. We got in contact with the developer that confirmed the fact that the fix was there but was not included in the release by mistake. And then the MVD, we contacted also the MVD, and in the end, the entry for this vulnerability was updated. On top of being error-prone, there is also a granularity problem. In fact, in here, Eclipse Mojarra is reported as affected product, but Eclipse Mojarra is actually a project, which is then releasing several packages. And developers, when they use dependencies, they actually import packages. And in this case, if we look at the commit, we can see that the classes that were modified are actually part of one single package, that is org glassfish JavaX faces. So we have a granularity issue, and so the idea could be, why not to maintain a finer granular mapping? Well, to maintain a fine-grained mapping is not that simple. If we consider all the packages in Maven Central that contain the classes that were modified in order to fix the vulnerability, so all the classes that were modified in the GitHub commit that we saw in the previous slide, we find more than 700 packages. In fact, it's not uncommon for a Java class to be rebundled in other packages, and I will talk about this a bit later. And then the number of indexed packages in the repositories keep on increasing. What you have in the slide is the growth for Maven Central, and you can see that year by year the number of packages that is published keep on increasing. And of course, there are new versions, but there are also completely new packages. So we believe that to maintain a mapping between packages and vulnerabilities does not scale. And to get away from this mapping problem, we devised our code-centric approach. So let's dig a bit in what we proposed. The idea is to go from vulnerability advisories to vulnerable code. So from CVEs in the MVD or GitHub issues or any other advisory, we look for the patch information. So we look for how the vulnerability was fixed with one or multiple commits in some repository. And then we look for the code that was modified. So method, constructor, functions that were added, deleted, or modified. And this is what we call vulnerable code. And then the detection happens by simply intersecting the vulnerable code with the code of any dependency of the application. If the intersection is not empty, then the vulnerability is reported. So it's sufficient that just one of the modified functions are present in one of the dependencies for the vulnerability to be reported. We evaluated the steady, so the tool implementing this approach, by comparing it with OWASP dependency check. We used 300 enterprise applications amounting to more than 75,000 dependencies. The results are in the table in the right. So in the category column, we have S that stands for steady, O that stands for OWASP, and then we have the subscript C and NC, which stands for code and no code. So we distinguish vulnerabilities whose fix requires some code changes from those that do not, because, for example, the fix is just a change in a default configuration. And of course, the code-centric approach works by definition on vulnerabilities that have code changes, but in Steady, we implemented a workaround in order to cover also vulnerabilities without code changes, but this is done basically using metadata again. So what is more relevant is to compare the results in terms of vulnerabilities with code changes. The first two lines of the table are findings that are common to both tools. So what is more interesting is what is in the blue square. What we find is that we have some unique findings for both tools, but in the case of OWASP, these are many more. And the number in brackets is actually the number of findings for projects where Steady could not run because the project was not building. And Steady requires the project to build successfully, whereas OWASP does not. With these findings, we review the subset of them in order to better understand what is going on. And what we found is that those reported solely by Steady were true positive, whereas in the case of OWASP dependency check, almost 89% of the findings are false positives. So indeed, we have some findings that are unique for each of the tools, so they complement each other. But the main differentiator is that in the case of OWASP, the true positive has to be found in the middle of many, many false positives. Once we have the detection, we can go beyond that because we focus on the code. So once we establish that that is contained, we can actually also ask ourselves whether this can be executed. And so what we do is to use both static and dynamic analysis in order to establish whether it can be executed. Because if it is, then there is a high risk, we assume that there is a high risk that the vulnerability can also be exploited. So we use static analysis by constructing a call graph. We use existing tools for this, like Suit. And we perform dynamic analysis, instrumenting either unit or integration test or both. This is how the findings look like in the web front end of Steady. As highlighted by the arrow, the same vulnerability may appear multiple times because the vulnerable code is included in different dependencies. And in particular, the first one is a package that is actually made of multiple Apache libraries. And this is showing the capabilities of the approach to detect the vulnerable code, no matter whether it is included and no matter the metadata. And then the red balls on the right are used to highlight whether the vulnerable code is reachable either statically or dynamically. By clicking on the findings, it's then possible to see which are the exact constructs or methods that are found reachable. So we use both static and dynamic analysis to establish reachability, and the two approaches complement each other. As you see in the graph on the right, we have the nodes in green, which represent constructs of the application, and the one in red, which is the vulnerable code. And we have paths with black arrows, which are those found with static analysis, and those in red, which are found by dynamic analysis. And as you can see, we have, for example, a path from method compress exploitability, which is only found by static analysis. And this may be due, for example, because of a missing test case. And vice versa, we have also a path which is only found by dynamic analysis because it makes use of Java reflection. So the two approaches complement each other. But this is not the only thing we do. What we do is actually to combine the two techniques. So let's see this with this example. Here we have an application that has a dependency on a framework, like struts, and it has a direct dependency, one direct dependency and two transitive dependencies. And the arrows that you see are those that are actually possible. And in particular, we have that the call from node 7 to node 11 is done using reflection. The nodes in red are the vulnerable code. And the vulnerable code in node 8 is actually not relevant because it cannot be reached. So if we use static analysis starting from the application, we find that the vulnerable code in node 10 is reachable. But the vulnerable code in node 2, 4, and 12 are false negatives. 12 because of reflection, and 2 and 4 because frameworks invoke the application rather than the other way around. And so because of the inversion of control, this vulnerable code is not found reachable. If we use dynamic analysis, the nodes highlighted in yellow are traced. Let's assume that those are the ones traced. And so at this point, we can also conclude that the vulnerable code in node 2 is also reachable, but still we have 2 false negatives, for example, because of insufficient test coverage. But if at this point we run again static analysis starting from the traced construct rather than from the application, at this point we can also find the vulnerable code in node 4 and 12 as reachable. So basically we combine the two techniques, and thanks to this we overcome the problems that comes out of dynamic invocations like reflection and inversion of control. The deep information we gained about how the application is using the dependencies can then be used in order to support the mitigation activities. In the table at the top, we show the so-called touch points, so calls from the application to the dependencies. And then we have a set of update metrics which are meant to support the dependencies in choosing among the different non-vulnerable versions of the library. In particular, we provide an information of how many of the APIs of the libraries that are used are still there in the non-vulnerable version. Then we have a measure of development effort, which is showing in how many places the application would need to be touched because what is used is not available any longer. And then we have two additional measures that provide the stability of the library. So in one case, we show the share of library which is reachable and that is still available in the non-vulnerable version. And in the last case, we provide this information overall. So how much of the library is still available unchanged in the new version. And in particular, these two metrics are meant to provide an indication whether an update would likely break the application or not because of major changes. And these are meant to support the developer in deciding whether to update, or if the likelihood of breaking is very high, maybe he can decide to fork the library and downport the fix, or to implement a safeguard in the application. So what are the takeaways for dependencies with known vulnerabilities? First of all, the CVE and MVD has issues. As we have seen, there is a granularity problem. There are also problems with the timeliness and the coverage, but no other publicly available database with comprehensive information is available. Code-based approaches reduce false positives, and they also support the impact assessment. But of course, it needs workaround to support also the detection of vulnerabilities without any code change. So vulnerabilities that do not have fixes that require code changes. And of course, they require a knowledge base with very detailed information at code level. The situation nowadays is that the information about vulnerabilities is scattered. Advisories, mailing list, and the like. So we do not have a central point where all this information is available. On top of it, to find the fixed commits is a very cumbersome task. There are some attempts at detect them using machine learning, but the human involvement as of today is still required. And it's not an easy task. So the result of this is that providers of vulnerability scanners are basically creating their own proprietary database in order to cope with the lacks of the MVD. But this does not scale, and the situation is paradoxical because we have open source software, but the vulnerabilities of open source software are not open. So this is the reason why we created Project KB. Project KB is an open and collaborative knowledge base for vulnerabilities with their fixes. So vulnerabilities are represented with statements, and they can be stored in Git repositories. And statements are in plain text, which is both machine readable and human readable. The idea is that each party can express its knowledge about the vulnerability and maintain his knowledge in his own repository. And then the data consumer may decide which repository to trust and how to reconcile the information. It also comes with tool support. We have KB in order to create, aggregate, and validate statements, and Prospector that supports the identification of the fixes for vulnerabilities. And work is ongoing on these tools. But the vision is that there will be security researchers, software companies, library maintainers that will produce the information about the vulnerabilities, and they will be publishing statements, and then there will be developers that use vulnerability scanners or researchers interested in doing research with real-world vulnerability data that consume the statements. Now let's move on to open problem, if this was not enough, and the direction. Together with the University of Paderborn, we studied how developers include open source software in the Maven ecosystem. And what we found is that on top of using the unmodified packages, by specifying the official, let's say, Maven coordinates like com.google, guava in version 23.0, they also use 4 different types of modifications. In the case of patched components, the source code is recompiled, usually because of some code changes like backporting a fix. And then the Maven coordinate is modified usually by adding a suffix to the version, like version 23.0 underscore fix 3. Then we have Uber jars, where multiple open source components are bundled together, and it usually gets a new Maven identifier, like com.myServiceBundle1.0. Then we have bare Uber jar, which is a Uber jar where all metadata are removed. And finally, we have repackaged Uber jar, which is a Uber jar, so a box containing multiple open source software, but the classes are repackaged, so the namespace are modified by usually prepending a string. We investigated the prevalence of this modification using 254 classes from around 250 CVEs affecting the most used open source software components at SAP. And what we found is that the most common modification in the components in Maven Central, which is the publicly available repository for Maven, the most common modification is Uber jar, which was found for 87% of the classes considered. And such classes were found in around 36,000 packages, belonging to 6,000 completely different Maven identifiers. Then we have also bare Uber jars, which are a popular modification. And then patched components were also found for 56% of the classes, and were part of around 6,000 packages. Repackaged Uber jars were found for 17 classes, so much less, which are part of 89 distinct identifiers, Maven coordinates. So this is a much smaller number, but it was also harder to evaluate this modification, as it implies a kind of distance measure, because the fully qualified name of the original class is modified once it gets repackaged. What we can conclude from this is for sure that such modifications has to be taken into account by vulnerability scanners, because they do occur in practice. So what we did next, of course, was to evaluate how the scanner performed. This is the result of running the scanners against a test suite that was created using the findings of Steady, OWASP dependency check, and commercial tool C3. So the findings were manually reviewed in order to discriminate true positive and false positives. And what we see from this table is that even for the unmodified case, the tools perform quite differently. For Steady, the precision and recall are 1 because the findings that were manually reviewed were all assessed as true positive, and there were no findings of OWASP TC or C3 which were not found by Steady. What is also evident from this table is that all the tools struggle with modified open source software, in particular when the metadata are not available, like for bare Uber jars. Also note that the test suite contains also vulnerabilities with no code fixes. And I would say that only scanners C2 and Steady provide a reasonable result in the presence of recompilation or lost metadata. But one conclusion that we can for sure draw is that managing known vulnerabilities is all but easy. And for sure, vulnerability scanner still needs to improve. But if to detect, assess, and remediate known vulnerabilities is so painful, wouldn't it be much better to just get rid of what is not needed? And this is the idea behind debloating. So the idea is to reduce the attack surface of an application by removing the code that is not needed by the application, because it could still be usable by an attacker, and it also needs maintenance. So this is the direction that we started investigating. We are still at a very early stage, and what we did until now is a case study in order to understand whether existing debloating tools can minimize the dependencies of an industrial-grade Java application. So we used a Java application with 260 classes, 62 test classes for a total of more than 400 test cases. And we had a total of around 2,500 classes coming from the dependencies. We used DepClean, Maven Shade, and ProGuard as debloating tools. And what we obtained, as you can see in the table, are very good numbers. So the tools were able to debloat the application down to 11 or 12 classes, and the tests were still successful. But we actually interviewed the developer of the application by showing our results. And what we found is that the tools were not able to handle a service loader definition, so a kind of dynamic programming feature that would have break some downstream application using the one we debloated. So the bloating seems promising, but still it requires to better investigate if it can really handle dynamic features and if it can be really used for industrial applications. So to draw some conclusion out of the entire presentation. For sure, what we can say is that open source software is omnipresent. Open source supply chain attacks are on the rise, and at the same time, dependencies with known vulnerabilities are still an issue. They are widespread, and the current scanners struggle to identify the vulnerabilities, especially in the presence of modified open source software components. Code level information, I really think is key, because it allows to increase the precision, and it also allows to get more insights on the usage of the dependencies. But gathering the information about the fixes on the vulnerabilities is an effort that is more likely to be successful if it's done in a collaborative way. And finally, reducing the bloated code is a very promising direction, as it can dramatically reduce the attack surface of the application, and I would say it is definitely worth investigating more. Thank you.